Good morning. Myself Muthumari, Assistant Professor of Mathematics, SFR College, Sivagasi. So in this session, we are going to see about the inner product spaces. So main objectives are, so here we are going to define inner product between any two vectors, and we are going to define norm of any given vector, and also we study the properties of norm. In usual three-dimensional vector space, V3 of R, it is possible to talk about the length of a vector and angle between two vectors. So these concepts of length and angle can be defined in terms of the usual dot product or scalar product of two vectors. So here it is a definition of inner product. So in any vector space, one can define an inner product between any two vectors. So here inner product is nothing but a function which assigns to each ordered pair of vectors to a scalar denoted by inner product of u comma v. It is a notation which is satisfying the following axioms. They are: inner product between u plus v and w is inner product of u and v plus inner product of v and w. The next axiom is inner product of alpha u comma v is inner product of u comma v into alpha, that is alpha into inner product of u comma v. And third one is inner product of u comma v is same as the conjugate of the inner product of v comma u, where v comma u is nothing but the conjugate, complex conjugate of u comma v. The fourth axiom is inner product of any two vectors is always greater than or equal to 0. If inner product of two vectors is 0, then definitely two vectors must be 0. So any vector space together with inner product defined on it is called an inner product space. So an inner product space is called a Euclidean space or unitary space according as F is a field of real numbers or complex numbers. So here is important note. If F is a field of real numbers, then condition 3 takes form inner product of u comma v equal to inner product of v comma u, since in real numbers conjugate same as the same number. So in these cases axiom 3 is similar. So axiom 3 asserts that inner product of u comma v is always real and henceforth is meaningful in this case. So next note is inner product of u and alpha v is alpha bar, that is alpha conjugate into inner product of u comma v. So whenever we are taking the scalar from outside of this inner product, it becomes this conjugate. So here is a proof. So inner product of u comma alpha equal to, so when we are changing the ordinate elements, it becomes the conjugate. So inner product of alpha v comma u, the whole conjugate. And so whenever the scalar is in the first ordinate, when we take it out from the outside, it becomes as it is. Whenever it is in the second ordinate, when we take that scalar from outside of the inner product, it will be like the conjugate. So in the third step, it is alpha bar into inner product of v comma u. In the next case, alpha bar, we write v comma u inner product, the whole conjugate, as inner product of u comma v. The next note 3, inner product of u and v plus w is inner product of u and v plus inner product of u and w. Here is the proof. So inner product of u and v plus w equal to, whenever we are interchanging the ordinates, conjugate becomes. So inner product of v plus w comma u, the whole conjugate. And by inner product definition, the axioms, we can split it up. Inner product of v comma u plus inner product of w comma u. And again conjugate properties, complex properties, a plus b the whole bar equal to a bar plus b bar. Like that we can split it up the terms. Inner product of v comma u conjugate plus inner product of w comma u conjugate. The next step, v comma u the whole bar is same as inner product of u comma v plus inner product of u comma w. So this is what we have to prove. Then inner product of any vectors together with a scalar, together with a 0 vector, the answer must be 0. So this is a proof. Next, here is an example for inner product space. So Vn of R is a real inner product space with inner product defined by, so we know what is Vn of R. First of all, n by n defined by, here inner product of x comma y equal to x1 plus y1 plus x2 plus x2 y2 up to etc. xn yn, where xn set of all n tuples and y is set of all n tuples and elements are from the real numbers. So this is called standard inner product on Vn of R. So to show that this inner product is an inner product, we have to verify all the 4 axioms we set above. So here let us verify this. So to show the first axiom, we have to take 3 elements from Vn of R and a scalar alpha. The first axiom is inner product of x plus y and z equal to inner product of x comma z and inner product of y comma z. So this is what we have proved in the first axiom. So inner product of x plus y comma z equal to, by addition in the Euclidean space, addition of n tuples, it will becomes inner product of x1 plus y1 into z1 plus x2 plus y2 into z2 up to etc. xn plus yn into zn. And after that, again by usual scalar multiplication, it will become x1 z1 plus x2 z2 up to etc. xn zn plus y1 z1 plus y2 z2 up to etc. yn zn. And finally, the first element is nothing but x comma z and the second one is nothing but inner product of y comma z. So similarly, we have proved all the three axioms. So similarly, we proved the second axiom, inner product of alpha x comma y is alpha into inner product of x and y. Similarly, we can verify the third axiom, inner product of x comma y is the same as inner product of y comma x. So inner product of x comma y is, by definition of inner product we have defined before, it is x1 y1 plus x2 y2 up to etc. xn yn. So we can commute x1 y1 as y1 x1 plus y2 x2 up to yn xn. This is nothing but inner product of y comma x. Similarly, the inner product between any two same vectors is, or inner product between any two vectors is always greater than or equal to 0, and inner product between the same vector is 0 whenever the vector is 0. This is the four axioms. So all the axioms you have verified. So we conclude Vn of R is an inner product space. Similarly, the next example, Vn of C is a complex inner product space with inner product defined by x comma y equal to, here we keep the first element as it is and we take the conjugate of the second element and multiply and take the addition of all the together. So inner product of x comma y is x1 y1 bar plus x2 y2 bar up to etc. xn yn bar, where x is n tuples element and y is also n tuples element. So next we check all the inner product four axioms for this Vn of C. So definitely it also satisfied. So first one is inner product of x plus y comma z equal to, by definition we have written, and then we, by scalar multiplication, we multiply each term with z, this conjugate of zi's. So finally we will get x comma z plus inner product of y comma z. Similarly, the second axiom also verified, inner product of alpha x comma y equal to alpha into, we have written the definition for inner product and then take alpha from outside of, because alpha is in every element, so we can take it at outside. So finally we will get alpha into inner product of x comma y. Next one, third axiom, inner product of y comma x equal to inner product of y comma x the whole bar equal to inner product of x comma y. So here we use the complex properties, complex number properties, z bar the whole bar is again z. So here we use that one and prove the third axiom. Similarly, we prove the last axiom, inner product between any two same vectors is always greater than or equal to 0, because we know the complex property z bar is equal to mod z square. So whenever we are taking the inner product between x and x, we will get x1 bar plus x2 bar up to etc. xn bar. Then x1 bar is mod x1 square. So it is a positive number. So whenever we are adding the positive number, the result is also positive. So that's why we get inner product of x comma x greater than or equal to 0. And inner product between any two vector is 0. Definitely that number should be, that element must be 0, because so when we are adding the positive numbers, the resulting gets 0, definitely each element must be 0. So by verifying the four axioms, finally we have proved Vn of C is an inner product space. Next, this is another example for inner product space. Here we are collecting the set of all continuous real valued function defined on closed interval 0, 1, and here we define the inner product space like this. So inner product between any two function they defined as is nothing but integral 0 to 1 f of t g of t into dt. So for this case we are next verifying all the four axioms. The first axiom is inner product f plus g and h equal to inner product of f and h plus inner product of g and h. So in the first line they are writing inner product definition. It is integral 0 to 1 f of t plus g of t into h of t dt. In integral property we know all these things, a plus b equal to, we can split up the integral a plus b equal to integral a plus integral b. Likewise we are separating the integrand, finally you will get the answer. And similarly second product also can be verified, because any scalar can be taken out from the outside of the integrand, because it is independent of the integrand, so we can take it out the scalar from outside. So finally we get inner product of alpha f and g as alpha into inner product of f and g. And third property, inner product of f comma g equal to inner product of g comma f. because here the field is real numbers. So in this case, inner product of f and g is equal to inner product of g comma f the whole bar, but the field is real number, so finally we get inner product of g comma f. And fourth case is also easy to verify. Inner product between two same functions is integral 0 to 1 f of t the whole square d of t. So here the instead of the function is positive, so after substituting the limits, the answer must be greater than or equal to 0. Similarly, if the inner product is 0, definitely that function must be 0 function. So by verifying all these axioms, we have finally proved the set of all continuous function and continuous real valued function defined on the closed interval 0, 1 is an inner product space. Next, definition. Here for a vector, we are defining norm or length. So what is norm or length? So norm is nothing but the square root of inner product between same elements. So here x is called a unit vector whenever their norm is 1. So next is an example. So for this function, that's for this inner product, we are defining inner product and norm. Here V is the vector space of all polynomial, the inner product defined. So we have to find the inner product between f and g. Also we have to find out the norm. Let's find inner product. So inner product of f and g is nothing but, by definition, it is integral 0 to 1 f of t g of t dt. F of t and g of t is also given in the problem. So we instead of that we are substituting, and after simplification finally, and after integrating and substituting the limits, finally we will get the answer minus 37/4. Similarly, we can find a norm. Is norm f equal to square root of inner product f comma f. So we find norm f square. So after using the definition of inner product and after simplification, we will get norm as square root of 19/3. Next is an important theorem. It tells the properties of norm. So already we defined norm. So what are the properties it behaves? It is norm is always greater than or equal to 0. If norm of any vector is 0, definitely that vector must be 0 vector. And norm of scalar into vector is same as modulus alpha into norm x. And third one is called squash inequality. That is modulus inner product of x and y less than or equal to norm x norm y. And fourth one is triangle inequality. Norm of x plus y less than or equal to norm x plus norm y. Okay, let us see the proof here. First one, by definition norm is it is square root of inner product of x comma x. So the inner product we have already studied in inner product always positive, but the square root of positive numbers is again positive. So from this we conclude norm x is always greater than or equal to 0, and if norm of any vector is 0, then square root of that particular number must be 0. Square root of number is 0 means that number must be 0. So definitely norm x equal to 0 implies x equal to 0. Second property, norm of alpha x equal to modulus alpha into norm x, right? That's what we have to prove. So first of all we are finding norm alpha x the whole square equal to, by definition it is inner product of alpha x and alpha x, and when we are taking the first term alpha, it become as it is. So alpha into inner product of x comma alpha x. When we have taken alpha from the second ordinate, it will become like its conjugate. So alpha bar into inner product of x comma x. So in complex number properties we know that z bar equal to mod z square. So here we are having alpha bar, it becomes mod alpha square into inner product of x comma x as mod x square. So finally when you are taking the square root, it becomes norm alpha x equal to modulus alpha into norm x. And third property is the inequality, right? Squash inequality. So whenever the both terms, either one of the term x and y are 0, it severely satisfies that inequality. So otherwise what we are going to do, that is what we are doing here. So we are considering an element, not an element, we are considering one identity z as y minus inner product of y comma x by norm x square into x. Of course inner product of z and z is greater than or equal to 0. So by using the definition they are writing the inner product between z and z, and after some calculation, finally we will be getting 0 less than or equal to mod x square mod y square minus norm x square norm y square minus modulus inner product of x comma y the whole square. So here we are using, to prove this we are using some complex properties, complex number properties. So finally we will get mod inner product of x comma y less than or equal to norm x norm y. The fourth one, modulus inner product of norm x plus y the whole square equal to less than or equal to norm x norm y. So norm x plus y less than or equal to norm x plus norm y. This is what we are going to prove. So for that first we find what is mod x plus y the whole square. So by definition it is inner product of x plus y and x plus y. Then after we are splitting each terms, and the first inner product of x comma x is norm x square, and keep the second term as it is, and we write the third term inner product of y and x as inner product of x and y the whole bar, plus last term is norm y square. And we know that z plus z bar is 2 into real part of z. So by that property we couple the second and third term, that is inner product of x and y and inner product of x and y the whole bar as 2 times real part of x and y. So which is less than or equal to norm x square plus 2 into modulus inner product of x comma y plus norm y square. So here we are using the term 2 into real part of z is always less than or equal to mod z. So we used that property here, and which is less than or equal to. So in the third axioms we have proved modulus inner product of x comma y less than or equal to norm x norm y. We use squares inequality here. Again binomial sum formula a plus b the whole square we used here. A plus b the whole square is equal to a square plus b square plus 2ab. By using this we get norm x plus norm y the whole square. So when you are taking square root finally we get norm x plus y less than or equal to norm x plus norm y. Thank you.